right, it is 10:30. Let's go ahead and get started. Welcome to Co-17A, specifically Co-17A for Dr. Diddell's 17A class. So if you are not taking 17A with Dr. Diddell, you're taking it with either Barn or Alameda or Lewis, you should really be attending the other Co-17A class that meets in the afternoon. So that's what I will say. You obviously can do whatever you want, but that is the choice I would encourage you. And the reason for that is because usually Dr. Diddell's class just does more stuff. Like he's going to cover things that the other classes do not. He's going to go more in depth on some topics. He's going to expect a few extra things the other class doesn't. And so we've just found over the years that the easiest way to handle that is for the students in his class to have kind of their own section of a co-class, and the students in the other classes to have their own section of co-class, if we have the manpower to handle that. So if you're in 17B with 17A, section B with Dr. Diddell, which meets Monday, Wednesday, Friday at, someone should know, 10 a.m., then this is the right place for you. If you're in one of the other three 17A classes that meet at a different time, Monday, Wednesday, Friday, I would really encourage you to do the afternoon class instead. I will also pass around, so I will be taking attendance. That said, you're also welcome to hang out for the moment if you want. You don't have to rewrite the sentence, but you can also come later. Probably gonna be very similar both classes today. I'm gonna hand out the attendance form. And this is for 17A, not for 16A or 19A. So please sign your name or write your name next to your name on it. It's alphabetical by last name. I will be, so part of this class is grading, most of this class is grading is based on attendance. So I will keep track of attendance so that I can pass or not pass at the end of the quarter. Everyone can pass, it's not too hard. You just have to come and occasionally do some of the reflections, which we'll talk about in a minute here. So yeah, let us go over the class logistics and eventually we'll do some math. Let's go ahead and take a look at Canvas here. Go. And of course, I'm doing this the wrongest way possible. Give me a moment. So for this, usually I have my screen extended, but I'm going to change it here so I can see what I'm doing while I do it. I'm going to go ahead and mirror my screens for a bit here. Let me change that up. And we'll change it back later on. Sorry, duplicate, not mirror. Apologies. Okay, yeah, but now it's super confusing. Yeah. Okay. Yes. Okay. Great. Cool. Hopefully this is, yeah, it'll be interesting. But I wanted to, why didn't you do the thing? Sorry, one sec. I wanted to duplicate, not mirror, not duplicate. Okay. Keep changes. Right on. Close that. That. Where's my zoom here? I'll make sure I'm sure. Okay, I guess, yeah, people will see this. Okay, so your Canvas dashboard, hopefully it doesn't look quite as full as mine does here because I got lots of things going on. I can look over here now, not over there. Let's go ahead and look at ours, which is the Co-17A one for Diddell. And something I like to point out to everybody the first quarter is that you can change what this looks like a little bit. You can change the color if you want to anything you like. And you can also change the nickname here to something else. So I usually like to write in like the day and time the class meets, sometimes even the location. So I might write in, like I might change this to, you know, Tuesday, Thursday, 10:30 to 12:30, 10:30 to 12, and then write like in, you know, 32:16. And you probably won't be able to see all that, but it can be useful depending on what you like to see there. I also sometimes write the CRN there because I find that information useful, but you might write something in there that you find useful or not at all. You can leave it as is. And let's go ahead and take a look at it. By the way, did I introduce myself? I don't know if I did. My name is James. You can call me James. Please call me James. But if you can't call me James, I understand. You can also call me Mr. Parmenter or teacher or instructor or professor, even though I'm not a professor, but I know that's what people like to say. Any of those is fine, but James is the best because that's my name and I like it. Let's go ahead and look at Canvas here. So for now, the homepage for our Canvas will be the syllabus. That'll change pretty soon, like probably by next week, to be the modules, because that's where anything useful is going to be found. But looking through the syllabus very briefly here. Yeah, the when and the where. Thank you, appreciate it. The when and the where of when we meet, you're obviously all here, so you know when and where we meet. Again, this is the Co-17A class for Dell's 17A class. I think we went through that. You are welcome to come via Zoom if that works better for you. You're also welcome to watch the class recordings later. But for those of you, so one distinction, there are some of you that are enrolled in the course, meaning you signed up for the course using the CRN with Schedule Builder. And then some of you are not enrolled, but in the Canvas because you filled out the Google form or you emailed me asking to be added. Both are fine. But for those of you specifically that are enrolled in the course, I am requiring that you come in person for attendance reasons. So if you're enrolled for one workload unit at the end of the quarter, you do need to come in person and fill out the attendance form. Thank you. If you're not, I would still love for everyone to come. I would love for everyone to come in person. That would be my personal preference because I just like seeing faces. I think it makes a better kind of classroom culture if there's more of us to talk to each other and do the things. There have been a few quarters where it's been like 3 people in the room and 15 people on Zoom, and it just was not as productive for everybody. So come in person if you can, but come any way you can if you can't come in person. As far as reaching me, email is typically the best way to get a hold of me. You can try calling my phone number. Sometimes I pick it up if I'm there. You can also come by my office. But really, the best way to find me in person is to look for me in my office hours, which you can find there. My office hours are these times and places. Starting, the drop-in starts not next week, but the week after next week. So the drop-in hours will start Sunday, October 6th, 7th, whatever, not this weekend, but next weekend. So this Sunday is, I think, the 29th. So the one after that's the 6th, I believe. And then next week, you can find me Monday, Wednesday, Friday, 2 to 4 in C class, which is the Center for Chicana Latinx Academic Student Success. It's in Memorial Union 210. If you go like up the stairs right by the flagpole there and just look slightly to your left, you'll see it. There's a big sign on the window. And then Tuesdays and Thursdays from 3:40 to 4:30, you can find me just downstairs in Dutton Hall, room 2258. What else? Yeah, so grading. The grading is pretty straightforward. Come to class, do the reflections, you will pass. If you're not enrolled in the class because you signed up with the Google form, you should ignore your grade completely. The grade you see in Canvas for this class is meaningless. You will not get a grade at the end of the quarter. None of it matters at all. So if you see like you're getting a 15%, you're not passing, it doesn't matter. If you are enrolled in the class, it does matter. So if you are enrolled, register with the CRN, make sure you pay attention to that. Again, I will try to update the attendance regularly so that your attendance score accurately reflects your attendance. Oh yeah, I think there's something I might need to, yeah, I'll take a look at that because I might need to mark them all zeros first so that it builds up. But yeah, as long as you're coming and filling out the form, it'll come out right at the end. So don't sweat it too much. If you feel like there's a mistake somewhere, you're welcome to let me know and I will address it. Also, in general, if you have, so unfortunately, the way I do things, this class is very much a hybrid, meaning they're not today, I don't think, right? There's no one on Zoom today. Let me double check. Can't see the things I'm trying to see. No, there's just me. I'm the only one. But there will probably be students on Zoom in the future. Now, yeah, share the whole screen. Welcome. But that means I'm kind of stuck here a lot of the time so that I'm writing things here where you could see them if you could see the thing right now, but you will see it on there. And also staying kind of in the camera. But I will also occasionally walk around, look at what you're doing, have you all work on stuff, try not to be talking the entire time. Because really, the way you're going to learn the math is actually by doing the math, in my opinion. What else here? Yep. If you do come via Zoom or watch the recording of the video at a later date, I would ask that you please fill out this attendance form, which looks like this. It's pretty straightforward. You put in your email, your ID number, your first name as it appears in Canvas, your last name as it appears in Canvas, and then the class you're attending, and then how you attended. I suppose live in person shouldn't really be on there anymore because live in person attendance, you're going to fill out this form, not this form. And then the date you are attending, the class date you are attending for. So like if you weren't here today and you watched the video that we're recording, say tomorrow, the date you would enter would still be today's date, September 26th, not tomorrow's date, September 27th. So the date for the class you're attending, which I will also write on the videos, so it should hopefully be easy to do that if you are watching this later. And then the date, and when you write the date, please do write the 4 digits of the year 2024, so that when I sort things later by date, things sort in the right order. It's not a huge deal to fix, but it will make my life easier if you fill this out correctly. And I know you want to make my life easier. Let's see what else we've got here. So you can find the videos. You will be able to find the class recordings in the modules as well as on my YouTube page, the YouTube channel for Co-17A. And actually, so I'll point out on the YouTube channel for 17A, you will see the videos for both this class and for the other section of 17A, which you might also find useful. I imagine most of the time the content will be pretty similar, but not always. Yep. Let's see, yeah, yep. And then there's all this other stuff here that's not super important. If you have any accommodations, you're welcome to use them. There aren't any tests or assignments in this class, so most of the accommodations people have aren't really necessary in this class. But if you want to be recording me, that's totally fine. The class is also recorded already, so if you don't want to do that, that's also totally fine. But really, whatever you want to do is fine with me. What else here? Where can you, so there's some notes about the class. Yeah, this class is worth 1 workload unit, which means it does count towards being a full-time student and any financial aid requirements, but it does not count towards graduation, which doesn't really matter because by the time you're graduating, you'll have 180 plus units, and this 1 unit is not going to plus unit. Where can you get more help? My office hours. Grant's website is a great resource. He's got lots of good handouts on there that I highly recommend looking at as you progress through the 17 series, 17A, B, and C. In fact, let's take a look at it for just a moment here. That's interesting. I'll fix that link later. But here's where you would go for 17A. There's lots of great handouts about all sorts of things. I often take notes from these handouts. There's a final practice down here. There might be a midterm practice in here somewhere. But yeah, there's lots of good stuff there. I definitely recommend taking a look at it. And there's tutoring. There's drop-in tutoring in the library on the lower level, Monday through Thursday from, I think it's 10 to 5, not 11 to 5. I'm gonna have to double check that. I think it's 10 to 5, not 11 to 5. And then Sundays, 3 to 7. I will be there Mondays and Wednesdays from 11 to 12. Grant will be there sometimes as well. It's mostly student tutors, but it's also occasionally specialists like myself and Grant and Jen. I don't think Sarah's down there at all. Yeah. And then there's also, of course, there's other stuff down there. There's chemistry, there's physics, biology, stats, econ, probably some other stuff too. Well, there's lots of tutoring down there. So if you're looking for help with the classes, other than math, it's a great place to go, as well as for math. And then, of course, you all, your classmates are great resources. You should study with each other. You should talk to each other. That is one of the best ways to learn things in college is by working with your classmates. So definitely get to know each other. Yeah, you should do that. Like next week, because we meet on Tuesday, I will see you in 5 days. Before class starts, talk to each other. Introduce yourselves. I guess we can do that right now, but well, we'll see. I feel like I should get through these things first. So any questions about the syllabus before we move over to the modules? supposed to be quiet. Like when you ask a question, you should be like quiet for a minute so that people can think about their questions. They're like, do I have a question? By the way, for those of you that walked in a little bit late, that's totally fine. But at some point, make sure you fill out this attendance form before you leave, and I'll make sure you do that. But okay, let's go ahead. And so the other kind of useful section of Canvas, which will be the homepage, probably starting next week, is the modules. This is where the useful stuff is. So literally the first part here is useful links. There's a link to the class attendance form, which I talked about, a link to the class Zoom if you want to come via Zoom. You can find my office hours. You can find my YouTube playlist. Also a link to the class notes, which I'll also probably be posting in Canvas, but if you want to find them a different way, that's also fine. Grant's website again, my website, which is trash. You can take a look at it if you want. There's really nothing useful there, except for a picture of me and my cat. And my office hours, my classes, some very small amount of handouts and links, probably nothing useful for this particular class. Yeah. So yeah, there's nothing great there, but I have to have a website apparently. So there it is. Oh, what did I just do? Terrible, terrible. Go away. Yeah, okay. Let's see what else here. And then there are some old video lessons from the various specialists, which you might, if you're looking for more resources, it takes a minute to load, but if you scroll down, you will see various videos on different things. I feel like some of these links are not super great. I don't know. We started doing this, then we decided we should put everything on YouTube, so we kind of stopped doing it. But there are some shorter videos here, whereas most of the videos that I post on YouTube are kind of lengthy because they're usually the class period. So if you're looking for maybe shorter, doses of content, that might be a good place to look. Oh yeah, so this is for later. We're talking about log or semi-log relationships. There's some useful handouts here, which when we get to derivatives, we'll probably go over this. That looks all right. Let's make this a little bit bigger. There, yeah, that's better. There are the old recordings and class notes, which are very lengthy, which is why I have minimized that, but you can see all my notes and videos from when I did 17A in spring of 2023. It's a while ago. Some exam prep materials, which there's nothing there right now. There'll be stuff in there later. Oh my God, go away. It doesn't want to go away. It's fine. Okay. The course evaluation, which is just like in the last 2 weeks of the quarter, that link will be live and you can fill it out and give me feedback. It's anonymous, so I won't know who wrote what. And usually my boss like takes all the Google comments and compiles them and sends them to me, but I won't know who wrote anything. So you can say nice things, you can say constructive criticism, you can say terrible things if you really want to. Really okay. You can be honest with your feedback is what I should say. And then lastly, textbook chapters. If you need quick access to any of the chapters of the textbook, they are right there. Feel free to take a look at them. Yeah, that's kind of the whole modules. Questions about anything in the modules? Right. Let's see, is there anything else in here that's important? So if you look at I guess we'll look at the grades for a second. So just so everyone can see what's going on here, there's the reflections. Oh, we'll talk about the reflections for a second. There's the reflections, and then there's the attendance. The attendance grades are out of 1. So you either get a 0 or 1 for coming or not. I will probably, not sure. I think I'll probably mark everything 0 to start off with. So your grade will look like a 0%. And then as the quarter progresses and you attend and do the reflections, your grade will build up to the final percentage that it is. Again, it's not a big deal. You're going to come, you're going to pass, it'll be fine. Also, if you didn't pass this class, it wouldn't be the end of the world. Not passing this class wouldn't affect your GPA at all. It might be an issue if you didn't complete enough units to be a full-time student. It would be on your transcript, but you know what? Nobody is looking at your transcript. They might look at your transcript if you're going to grad school, maybe a little bit. No one's going to care that you didn't pass the 1 unit workload class if you still passed your 17A class. But really, in life, no one is looking at your transcript ever. So they might look at your GPA, Maybe for your first job after college. Definitely for grad school. But other than that, they just care that you got a degree. They don't really care what your transcript looks like. All right. So what else here? I feel like there was something else I wanted to say. Oh yeah, the reflections. So look at the assignments. The reflections are pretty easy to do. Here's the first one. I just want to know things about you, really. There's no math questions in these reflections, except the only math question is, what did you do in your math class this week? And this first one doesn't even have this. So like this first one, your name, where you're from. I didn't change it. Did I not change this? No, I guess I did. Okay. I feel like I didn't. No, sorry. I thought I changed this question, but I guess I didn't. And you can always tell me a joke. I love some jokes. I don't tell jokes well, but I like hearing them. Let's look at the next one because I feel like the next reflection is a little bit more indicative of what they will all look like. Go back to the assignments, I guess. So here's the second one. So what did you cover in your class? The actual class, not this class. How would you evaluate yourself, or what grade did you give yourself in your Math 17A class this week? Anything you want to see me cover in the coming week, that one I really pay attention to, because people say all sorts of things like, James, really like you to talk about limits or derivatives or specifically the product rule or something like that. So if you have things you want me to talk about, that is a great place to say them. You can also tell me other places as well, but I'll definitely be looking there usually on the weekend before, like, or on Monday before our class on Tuesday to see, oh, the students would like me to talk about this week. So definitely answer that. And then usually some question like about you or about something you like. This week, it's what is the story that you really enjoyed? I'm thinking book, but it could be a graphic novel, video game, something else completely. So really, I just want to get to know about you a little bit. And yeah, they're easy to do. They take maybe 5 minutes, 10 minutes at the most, I think. You shouldn't be spending a lot of time doing this, right? You should be like, yeah, we did this, and this in class. I'd like you to talk about this. I'm doing this well. And yes, my favorite book is, I said it was recently, The Last Graduate by Naomi. Oh, that's a good book. It takes 3 books actually, but highly recommend reading it. It's like Harry Potter, kind of, and then it's about students at a magical school, but it's better. It's way better. You should read it. I highly recommend it. Yeah. All right. I think that's all I've got to say about class logistics. So I'll say again, any questions? Okay, let me close this. Yeah, sure. Close this. I don't need that. Yeah, cool. Close this. Let me change my view back to the typical view I like to have. Sure, somewhere. Yes, right there. Maybe today, ever. Okay. Display. Let's do that. Let's extend these displays instead of duplicate. Right on. Okay, let's close that. Put that over there. Big. This. Come on, Zoom. Where'd you go? Oh, there you are. I hate the little Zoom thing is always hiding. Okay, there you are. Make sure I'm sharing the right screen here. Okay, sharing screen 2. So later on, if you decide you want to look at the video for whatever reason, because I said something, you're like, I don't know what we said, or you just want to review something, the view you will see will just be like this and my disembodied hand. And I guess you'll see my face up in the corner probably. Let me click on it. If you, by the way, if you're looking at this, 2 things. One, if you see the little like menu items on there, let me know so I can click over here so those aren't on there, because I think it's annoying to look at those. And 2, if I'm writing something like down here and I'm writing and let me know that I'm off the screen, because it'll happen. It's unavoidable because I move the paper around a whole lot. Oh, and I guess thirdly, if the cursor is over there, you can tell me too, because I think it's terrible that it's over there. All right, it is almost 11. We are in class till when? Yeah, 12, well, 11:50, right? 11:50. I could probably set an alarm for that. I guess I should, yeah, there's not so many of you that I couldn't possibly get to know your names. So let's have everybody tell me their names, starting with this side. What's your name? Serena. Janima.
Bronson.
Bronson.
John Carlo.
John Carlo.
John Carlo.
Both John Carlos, yeah, they're both the same last name as well. Awesome. Sorry, Emma? Emma. Cat. Say one more time. Snyder. Jennifer. Simmer. How you spell it?
Simran.
Cool, Simmer.
Michaela.
Beckett.
Liv.
Leila.
Ricardo. Yeah.
Say it one more time.
Yeah.
Gat. DAT, okay. I don't promise to know your names, but with enough practice, I might get to know them. Depending on what attendance looks like, we'll see. If you come see me in office hours, I will more than likely get to know your name. But it's always hard in fall quarter because there's so many students. All right, I guess we should talk about math. I mean, that's what we're here for, right? Okay. So yesterday in Dr. Adele's class, he said a few things. It looked like he mostly talked about numbers and functions and domain and range and piecewise functions and odd versus even. Yeah, okay. So, yeah, where to start? I guess I should write some things here, like this Co-17A for Adele. And today is September 26th. Yeah, September 26th. So first, I guess we could talk about numbers for a second. Numbers, yeah, okay. So, depending on who is saying things, different teachers kind of have different expectations about what you know coming into class. One thing they might expect is some familiarity with certain notations. The ones that are probably most likely to come up with Dr. Adele, and the numbers are these symbols. This funky kind of capital N, or I call the fancy N. This is for the natural numbers, also known as the counting numbers. Some people say the natural numbers include zero. Some people say the natural numbers don't include zero. I wouldn't worry about it either way personally. I would just say they're 1, 2, 3, 4, 5, etc., and maybe 0. I feel it, yeah. And then we have fancy Z for the integers. Integers are just the positive and negative natural numbers and 0. So it's everything from negative numbers, -4, -3, -2, -1, 0, 1, 2, 3, 4, so on, so on, so on. And my Z looks not the best. And then we have the fancy Q for the rational numbers. Why a Q? Because I think Q is for quotient, and a rational number is a number that can always be expressed as the quotient of two integers, or the fraction for that word. So numbers like 3/5, 1/2, 9/7, 0.23, any number that can be expressed as the fraction or quotient of two integer numbers. I know that last one isn't written that way, but any terminating decimal can always be written as a fraction. 0.23 definitely could be written as 23 over 100. Also, and so I should say, any rational number can either be expressed as a quotient, like I've said. You can also write it as a terminating fraction or a fraction with a decimal that repeats eventually, like 0.33333 forever, or 0.19191919, right? Both of those are numbers that could be written as fractions as well, just to figure out how. And then he didn't mention this one, but I'm gonna say it anyway. capital I, funky looking I, for the irrational numbers. You don't encounter this one as much, to be honest, because usually we don't make a distinct, or we don't really care about just the irrational numbers, but the irrational numbers are ones that cannot be written as the quotient of two integer numbers. Something like the square root of 2, or pi, or e, or the square root of 3, or the cube root of 7. The list goes on and on and on. All these numbers you can either think of as not being able to be written as the fraction of two whole integer numbers, or you can think of as they are numbers that have a non-repeating, non-terminating decimal expansion. Pi, right, goes on forever. Square root of 2 goes on forever. Never repeats, never ends. And finally, the one we care about the most, I think, is fancy R for the real numbers. So that's basically all of the things we just mentioned all in one. It's all the rationals, it's all the irrationals, all the numbers. Well, all is probably not the right thing to say there. Because there is one, well, I mean, there's one more that we care about, which you will talk about. We won't talk about in this class, really. But when you get to 17B and 17C, you will talk about imaginary numbers, also known as complex numbers. So there's complex numbers, which includes imaginary and real numbers. I should also point out that the rational numbers include all of the integers. You could write any integer as a non-terminating decimal, right? Excuse me. 2 is a non-terminating decimal. It's 2.0 if you really want to write it that way. So every integer is a rational number. Every integer is a real number. Every rational number is a real number. Every irrational number is a real number. Real is a terrible name, by the way. And here's why. I was having a discussion with a student one time, and I was trying to help them with reals versus imaginary numbers. And the language we were using with it, they were getting confused because they really thought that like the not real numbers didn't exist. And non-existence would mean like they were kind of thinking of it as like it really like it was not a thing that ever existed in the world. So there's a type of mathematical non-existence where we say, well, this thing doesn't exist in the mathematical sense, but the concept of it is still something that is existing. So imaginary numbers or complex numbers aren't real numbers, but they do exist. There is a concept of them that we will talk about, not this quarter. So those are the numbers. We're going to stick mostly to these. And also, I mean, all of these above it because they're all included in there. Most of the time we're talking about integers because they're easy, but a lot of the times we're talking about irrational and rational numbers. I should also say, I think I said this before, I'm gonna say it again. I'll say it often. You're always welcome to ask questions or for clarification. If there's something I said that doesn't make sense, or you just have a question that I haven't addressed about the thing we're talking about, speak up. I am really, really happy to talk more to answer questions. Let's talk about functions. Wow, let's talk about writing more legibly. Okay, I'll do my best. But that also, if something is hard to read, don't hesitate to ask me what I've written. It's usually the words I just said, but occasionally I write something like, what is that? Also with numbers, sometimes my 4s look like 8s or other terrible 5s look like 3s. So if you're not sure about something, really, 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 it's okay to ask. I will not be offended. I know my writing is mediocre. My penmanship is mediocre. So functions. What is a function? What is and is not a function? Very generically, a function is a rule that assigns one and only one output to any input. So an example of a function would be f of x equal to x squared. because each possible input value x gets assigned to only one output value, in this case, the square of that number. So some possible inputs and outputs are f of 0 equals 0. F of 1 equals 1 squared, which is 1. F of 2 equals 2 squared, which is 4. F of 3 equals 9. F of negative 1 also equals 1. F of negative 2 also equals 4. F of negative 3 also equals 9. I'm picking easy numbers, but you could plug in anything, right? You could say f of pi is pi squared, or f of the square root of 7 is the square root of 7 squared, which is going to be 7. But the whole point is here is that anytime I plug in one number, I get out only one number. I don't get out two different possible results. That's the defining feature of a function. You might view this graphically as passing the vertical line test. So if I were to graph this function, it looks like your standard, everyone's favorite parabola that opens upward and goes through the origin. And notably, this graph passes what we call the vertical line test. Any vertical line I draw passes through at most 1 point on the graph, which is the same as saying any input of x, say like this is 3, only has one corresponding output. Or if I have input, say negative 2, there's one corresponding output. That's the whole idea with what a function is. There was something that crossed my mind there as I was saying that. Oh, I know what it was. Just as a quick aside here, graphing is an important skill, which we're going to work on in this class. I would also highly recommend becoming familiar and comfortable using Desmos. It's a great tool. I think you should all use it. Not that you should still be able to graph things without using it, but it's good to use it to see how things should look, to check your work. I love it. Yeah, okay, so there's an example of a function. Okay, question. Would I say that? I don't know. I mean, so it is certainly the calculator I like the best. If I were to purchase a graphing calculator, it is the one I would pack, like an 83 or an 84. They're both perfectly good. You can, I don't know how long for, but you can check out a TI-84 from the library. I don't know, I think it might be only for use in the library, but still that is a place you can certainly borrow it. Or maybe what I would say is borrow it to see like if you like it, right? Like maybe you haven't used one, you're like, well, I want to see if this is really worth spending. I don't know how much it costs, like $100 still. Yeah. It cost like $100 when I was buying them 20 years ago. Like, you think they would have come down in price, but I guess not. But do you really need a graphing calculator? I don't know. I don't think so. Like if it was just like, if it was free, I'd say yes, everyone should have one. If it didn't cost $100, yes, I would say everyone should have one. But you've got a phone, you can use Desmos on your phone. So I would probably say you don't absolutely need one. If you happen to have one, that'd be great. But I don't think you need to purchase one. But also, if you're in the library, you totally should check them out from the library because they definitely have them and like nobody checks them out hardly ever. So they have TI-84 something like plus or whatever, I don't know. And they also have a TI-30X, I think, which is like the scientific calculator, which is also a good calculator. So those are both available to check out in Shield's library. But I don't think they can leave the library. I think you have to return them before you leave the library. But still, library is a great place to study, do math. So cool. All right, let's look at some not functions. So probably the most typical example of a not function is a circle. So for example, the circle x squared plus y squared equal to 25. And my favorite circle to draw. That is the equation of a circle. It's centered at the origin and has a radius of 5. That's a okay circle here. So it's got like the point 5, 0. It's got the point 0, negative 5 and 0, positive 5. You want a more fun point, it's got the point 4 comma 3, and 4 comma -3. The problem, well, not the problem, the thing that makes this not a function is that there are some values of x, and I should say, in this class exclusively, we are thinking of x as the input and y as the output. So here you would say, well, y can't be a function of x here because some inputs have more than one output, right? If x is equal to 4, then we get two different values for y. We get y equal to +3 and y equal to -3. Or in other words, we are failing the vertical line test. This line, what is that line, by the way? I should ask that question better. What is the equation of that line that goes through the point 4 comma 3 and the point 4 comma -3? Something is 4. What has to be 4? So close. But let me point out, which coordinate is 4? Is it the x coordinate or the y coordinate? It is the x coordinate. It's okay. It's fine. It's fine to say the not right thing. Everyone might have been thinking it. It's okay. Like y equals 4 is often the right answer. But here the answer is x equal to 4. Which makes sense, right? Because we're saying, oh yeah, if x equals 4, we're getting y equal to 3 and y equal to -3. So really this idea of passing or not passing the vertical line test and an input having or not having more than one output, literally the same thing. It's just viewed in a different way. So not a function. How would you know it wasn't a function if we hadn't graphed it? Like what if we just said, what if we covered this up and said, okay, tell me, is this a function or not? Is a function, and really I should be more specific, is a function of x. Meaning if we input one x value, do we get only one y value or multiple y values? Yeah.
So you could isolate one variable and then you would find that there are two equations. So it'd be
Right.
like y equals plus or minus 25 minus x.
Exactly. Plus or minus the square root of 25.
Yeah.
Yeah. And specifically, we do have to, if we're talking about being a function of x, then we're always looking to isolate y. Because y is the thing that's the function, and x is the independent variable that we are the function of. So exactly what was it Giancarlo said, we get y squared equal to 25 minus x squared. And then when we take the square root of both sides, we have the square root of y squared equal to the square root of 25 minus x squared. There isn't a plus or minus in there yet, but there's about to be, because fun fact, maybe not a fun fact, a fact, the square root of y squared isn't just y. The square root of y squared is actually the absolute value of y. We'll talk about that in a second. But what that means is the absolute value of y is equal to the square root of 25 minus x squared. And quick to the side here, if the absolute value of y is equal to 7, what does that mean y could be? What's one thing y could be? You can just say it, you can just shout it out. It could be -7 or it could be +7. So when you have the absolute value of something equal to some quantity, that means that something can either be the positive or negative of that quantity. Well, the same thing is happening right here. This means that y can be plus or minus the square root of 25 minus x squared. So if it's exactly, whoops, I'm kind of off. See, I'm getting a little crazy there. Exactly, if x were to be 4, for example, then y would be plus or minus the square root of 25 minus 4 squared, which is plus or minus the square root of 25 minus 16. 25 minus 16 is 9, and plus or minus the square root of 9 is plus or minus 3. So one x input is giving us two different y outputs, and that's the hallmark of not being a function. But really, you don't need to plug in a value to see that. Once you get to this plus or minus here, that is the one of the telltale signs that's not a function, because your one x value is giving you two different y values. Sorry. Okay. Let me go back for a second, not back, but let me address for a second the thing I said about the square root of y squared being the absolute value of y, because I feel like that's something that people are often kind of like, what about? So here's why that's true. So here's the square root of y squared. In fact, let's just look at the numbers. What's the square root of 5 squared? Well, what's 5 squared? What's the square root of 25? Right. Easy. Okay. How about the square root of -5 squared? What's -5 squared? Oh, positive 25. And what's the square root of positive 25? Still just 5. So either way, whether we input a positive value for y or a negative value for y, we still end up with the corresponding positive value. And the function that does that is also known as the absolute value function. So it's really, really true that when you take the square root of a variable squared, you end up getting the absolute value of that variable. Sometimes it's not really important, but sometimes it's super important. So when we're solving something like y squared equal to 25 minus x squared, the shortcut is that we end up getting y equal to plus or minus the square root of 25 minus x squared, because we know that's what happens when you square both sides. But the intermediate work is really saying, oh yeah, the square root of y squared, we're just square rooting both sides, is the square root of 25 minus x squared. But then the square root of y squared is the absolute value of y equal to the square root of 25 minus x squared. And then the absolute value of y ends up meaning that equal to this means that y is going to be plus or minus whatever's inside, or whatever's over on the right hand side there. In a similar sense, just so everyone feels okay with it, it's why when you're solving something like x squared equal to 9, you end up getting 2 answers. I mean, we should get 2 answers, right? 3 squared is 9, but -3 squared is also 9. So the solution should be x equal to plus or minus 3. Again, the short way of solving this is just saying, oh yeah, the square root of x squared is equal to the square root of 9. So x is equal to plus or minus the square root of 9, which, yes, we should write as plus or minus 3. But really kind of the intermediate step that we're not writing down, you don't need to write down, but it's still important to be aware of, is we're really saying, oh yeah, the square root of x squared here really means the absolute value of x. And the square root of 9 is what? Right, just 3. But then the plus or minus is coming from the fact that, oh yeah, if the absolute value of x is equal to 3, that means x can be positive 3 or negative 3. That's where that's coming from. So really, really important to know that when you take a square root of a number, you only get the positive result. It's when you're solving an equation like this that you have to toss in the plus or minus to get all the solutions we need. It's a little funky. Questions about that? Okay. So we've talked about what makes a function, what makes something not a function. Yeah, we should cover that too. Continuing with the functions for a minute, even though I don't think this was talked about in class, I think it's still important because it is going to come when we talk about finding the inverse of a function, which is something we will certainly be doing in this class. What is a one-to-one function? And that's a 1-1 for 1-to-1. It looks kind of like an H, I know. This is 1, 2, 1. So let me give you an example of something that's not a 1-to-1 function. So here's a not example. F of x equal to x squared is a function, but it's not 1-to-1. And the reason it's not 1-to-1, or what makes it not 1-to-1, so what I should say is, to be 1-to-1, each input, that's the wrong way to say it, James. Each output corresponds to only one input. So let me show you why this function is not 1-to-1. Graphically first. Somebody picked a nice y value for me that's a square number. Someone tell me your favorite square number. 4, great example. So here's the line y equals 4. And how many x values on that, show me on your fingers, how many x values are there that correspond to that one y value? Yeah, and they do happen to be the number 2 and -2. Oh, well, sometimes things are a little too corresponding. So here's x equal to 2, and here's x equal to -2. So this function is not one-to-one because there are 2 different x values that give the same output y value. Why do we care? We care because if you wanted to find the inverse of this function, the inverse would not be a function. So the way you find the inverse of a function is typically by interchanging the x and y roles and solving for y. If you interchange x and y here, y equals x squared, let's interchange them. X equals y squared. Oh no, x equals y squared. Looks like the parabola, but opening to the right. Is that a function? Definitely not. It fails the vertical line test. So for a function to be invertible, it has to be one-to-one, so that its inverse passes the vertical line test. Or another way to say this is a function has to pass the horizontal line test so that its inverse passes the vertical line test. So being one-to-one is the same as passing a horizontal line test, meaning any horizontal line passes to the function at most one time, which this function is not meeting. This function is not one-to-one. Yes. So we're not doing the inverse right now. Although, so I will say the way you do the inverse is by switching x and y and then solving for y. So I didn't complete the process here, but I will point out that if we solve for y, we would get y equal to plus or minus the square root of x. But again, this one really isn't a good example of finding the inverse because it's not, the inverse is not a function. And for a function to be invertible, its inverse needs to be a function. There's something else I want to say here. Oh, so I should say this example is very reliant on our general assumption that x is always the independent variable and y is always the dependent variable that's the function. It is perfectly cool to say in later classes, oh yeah, this is a function where x is a function of y. That's not what we're doing in this class, but later on, like in 17b or in 17c, you might say, oh yeah, this is a function of y, or this is a function of x. You might change up what the independent variable is. So for now, this is for sure not a function because y is not a function of x. It's failing the vertical line test. But later on, that becomes something we have to be a little bit more careful about. What is a one-to-one function? Well, there's lots of examples. What's my favorite example? I have 2 examples. So here are 2 functions that are one-to-one. Sure. First example, f of x is equal to x cubed. Kind of a classic example of an odd function that's one-to-one. This is not my favorite one to draw. It's kind of like this. Flattens that right to the origin there for a second. It's like that. This function is one-to-one. Any y value you picked, there would only be one x value that corresponded to it, right? If I pick y equal to 8, also just as a kind of note, I will use y and f of x pretty interchangeably. Right? I know that I said f of x equals x cubed, and I'm saying y equals 8 instead of f of x equals 8. People do that all the time. Get comfortable with it. But if we pick y equal to 8, then we're saying, okay, well then 8 equals x cubed, and x is going to be the cube root of 8, which is 2. And there's only one cube root of 8. It's only 2. Or if y was -8, -8 would equal x cubed, and x would be -2, which makes total sense, right? Here's y equals 8, here's x equals 2, here's y equals -8, here's x equals -2. And you can see graphically that any horizontal line I were to draw would exactly pass this graph in one point, no matter where I drew it, right? horizontal line here, or here, or here, or here, or here, or here, or here, only passing through one point on the graph. Which means it's invertible. And I guess we could find the inverse. So here's how you find the inverse. Typically, you rewrite it with a y instead of a f of x. So step one, right, y equals x cubed. And the next couple steps, the order kind of doesn't matter. I am a fan of interchanging x and y first and then solving for y. Some people like to solve for x first and then interchange them. Doesn't matter what way you do it. So I'm going to interchange x and y and then solve for y. I'm going to solve for y by taking the cube root of both sides. Unlike a square root, where when you square root both sides, you need to throw in a plus or minus. That is not true for any odd root. Odd roots don't get a plus or minus. So I take the cube root of both sides. The cube root of y cubed is just y, not the absolute value of y. So my inverse function is y equal to the cube root of x, or f inverse of x equals the cube root of x. Or if you prefer, f inverse of x is equal to x to the 1/3. And there is a very, very nice graphical correspondence between a function and its inverse. The inverse function looks exactly like the original function, has been reflected in the line y equals x. This is a great time to use Desmos, so you can see how nice it looks and how really reflective it is. In fact, why would I draw it when I could show it to you? So not that my drawings aren't good. Sometimes they're good, sometimes they're less good. But looking at Desmos here, I'll just point out, right, you've got your y equals x cubed. Awesome. And you've got your y equals x to the 1/3. Inverses. And just in case you want to see it, here's a y equals x as well. So you can see, oh yeah, these graphs really are reflections of each other, right? If you take this blue graph and reflect it across the line y equals x, you get the red graph, and vice versa. The same is true for the other function I mentioned, right? If you look at y equals x squared and x equals y squared, even though x equals y squared isn't a function, you still have the same graphical relationship. If you take y equals x squared and you flip it across that green line, you're going to get the other graph, which is kind of nice. So occasionally, someone might ask you to graph the inverse of something just using this graphical fact. They won't give you the equation, but like, here's a graph its inverse by reflecting it across the line y equals x. Didn't really mean to talk about inverses that much, but it's okay. They're important. All right, let's see. So 1-to-1, cool. Where was it going? Oh yeah, I think we're gonna talk about domain next. Yeah, let's talk about domain. Unless there's any questions about anything I've said about this. So I know I don't really need to stop for questions because you're always welcome to ask them, but it's just a habit that I've gotten myself into that I can't really help. So I will try not to stop and ask the question too often because it's kind of pointless sometimes, but sometimes I just can't help myself. Cool. Let's talk about domain and maybe range a little bit. Domain is more important, I think. And what I would say is, yeah, what am I saying? We're going to talk about implicit domain, I guess, which isn't really, you don't really know about it, but something, so I'll say sometimes there are functions that have an explicit domain, which means you've been given some function and told that the input has to be between certain values. For example, if I said that this function p of x equal to x squared plus 3x plus 5 represented the amount of profit for producing X grams of product, then even though this function, without all the information, has a domain of X could be any real number, right? You can certainly plug in any real number to that function and get a real output. But there's an explicit domain of, well, because of the context here, X certainly shouldn't be negative. You can't make a negative amount of grams of something. So here, the explicit domain would be everything from, I'm gonna write a couple different ways, would be X being greater than or equal to 0, because you could produce 0 grams, right? I guess. And this function is totally made up. So, right, like it probably wouldn't make sense that you're gonna have a profit of $5, I guess, for making 0 grams, but we're not worried about that. But the better way to write this domain is using interval notation, bracket 0 to infinity. Even though without context, if I just said, hey, here's a parabola, x squared plus 3x plus 5, then the domain would be all real numbers. So sometimes the context can affect what the domain is, but much of the time in this class, we typically just default to look at the function and tell me what the domain is. Don't worry about any context. And then maybe if there's context later, we'll adjust it. So that's usually the kind of place we're coming at domain from. It's just we're looking and seeing like, okay, is there anything that X is not allowed to be? In this example, no. Here you might write domain like this. I would, but some people like to write it using the fancy R because the domain is all real numbers here. And that's going to be true for any polynomial function. So if your function was, say, g of x equal to x to the 17th power plus 5x to the 4th minus 3x squared minus 2x minus 1, that's a polynomial. Every power of x is a non-negative integer. That means it's a polynomial, and there are no domain restrictions. X can be anything because x to a positive integer power, sorry, any number to a positive integer power is always defined. Yeah. So domain is the same. It's all real numbers. Everything from negative infinity to infinity. We're obviously not including negative infinity to infinity because they're not actual real numbers that we can include. They're just saying you go, whoops, don't trip on it. You go way that way and you go way that way and you get everything going that way or that way. No matter how far you go. On the other hand, some functions do have limited or restricted domains, and there's typically 3 types of things. Yeah, 3. There's 3 types of things we see where that limit what the domain could, oh my God, could be. So there's a couple of examples. Let's look at this one. Paper, come on, paper. So let's look at this function, say f of x equal to 3x plus minus 6 over x squared minus 5x minus 24. So this function is a quotient, the rational function. And for any function where you have division, we have to avoid division by 0. So for this function, when we start talking about domain, we have to exclude any values where the denominator is equal to 0. Those can't be in the domain. So in this case, we're going to factor that. I think it factors as x minus 8 times x plus 3 equal to 0. Yeah, because negative 8 times 3 is negative 24, and negative 8 plus 3 is negative 5. Works out. So x equal to 8 and x equal to negative 3 are out of bounds. We cannot have those as values that we plug into this function because you'll get division by 0, which is undefined. So here our domain, I'm going to write it on the number line first. I don't want 8. I don't want negative 3. But I want everything else. So my domain here is going to be all real numbers from negative infinity to negative 3, exclusive of negative 3, use the parentheses. And then union with everything from negative 3 exclusive to positive 8 exclusive. And then union everything from positive 8 exclusive and onward. There's our domain, just plucking out the points that we don't want. And that's typical of functions where you have division by potentially 0. I should do one more example of this because there's one other thing I want to address specifically. Let's say we had something like, g of x equal to, what do I want here? Yeah. X squared minus 4 over x squared minus 5x plus 6. Is that what I want, James? Yes, that's what I want. So what I want to point out here is that it is a mistake to factor and cancel things, specifically the canceling, before thinking about domain. So if you factor this, I will point out you get x minus 2 times x plus 2 on the top. And on the bottom, you get x minus 2 times x minus 3. And if I was going to graph this or do any, or find the derivative or anything else here, I would cancel the x minus 2. But the one thing I really can't cancel this for is finding the domain. So here, the domain, I have to exclude both x equal to 2 and x equal to 3. 3 is a no-brainer. 2 maybe feels a little bit like, well, couldn't we just cancel those out? No, we can't. So what's happening at 2 is you have the function actually as a whole, which we'll talk more about when we get to limits. But for now, trust me in that when you're finding domain, you have to find the domain of the original function before you simplify or cancel anything. So here the domain would be everything from negative infinity to positive 2, union positive 2 to positive 3, union positive 3 to infinity. Okay. So that's one type of domain restriction where you have potential division by 0. We have to exclude any numbers that make the denominator equal to 0. I should say any values of x that make the denominator equal to 0. There are two other types of functions that have domain restrictions. Let's look at the next type. Let's say we have, sure, something like f of x equal to the square root of, what do I like here? Sure, 49 minus x squared. Oh, thank you so much. There you go. What is the domain? So the question we're really asking is, what kind of numbers are we allowed to take the square root of? Positive numbers and also 0. So on the other hand, we cannot take the square root of any negative number. At least I should say. So when we're talking about functions and domains, the question that's being stated that's not always said is, what numbers are you allowed to plug in so that we get real results? So we can't plug in any negative, or we can't take square root of any negative numbers because square root of a negative number is a not real number. It's imaginary complex. So we're not always going to say those words, but that's always what's implied is what can we take a square root of so that we get a real answer, because these are all real valued functions, even though no one is saying those words. So we need the argument, what's inside the function, of the square root, or any even root, right? It could be a 4th root or a 6th root or a 1000th root. Any even root, you can only take an even root of a positive, I should say non-negative number. Odd roots are not, that's not the case. Do we need the argument of the square root to be non-negative? In other words, we're going to set the argument of the square root to be greater than or equal to 0. And I would just say, right, the argument in this case, the argument of the square root is 49 minus x squared. It's the thing that is inside the square root. And then we have to solve this. And yeah, it's dicey. You could probably get away with bringing the x squared to the other side and square rooting both sides and using an absolute value. Not what I would recommend. It's also not going to work out well if this quadratic is more complicated than just a square minus another square. The safer route to solving inequalities like this is to have 0 on one side like we already have, and then factor the other side as completely as possible. So here I'm going to factor the 49 minus x squared as 7 minus x times 7 plus x. And I should stress, it is 7 minus x and 7 plus x, not x minus 7 and x plus 7. I will point out that x minus 7 times x plus 7 is equal to x squared minus 49, which is different than 49 minus x squared. I point that out because often people will want to factor it this way, even though it factors that way. And whenever you're factoring a difference of squares, it's always the square root of the first thing and the square root of the second thing in that order. So if you have a squared minus b squared, it's always going to factor as a minus b times a plus b. If you have b squared minus a squared, it's going to factor as b minus a times b plus a. Yeah, the second term is the same either way. The first term is not the same either way. A minus b and b minus a are opposites of each other. So be careful. So then solving this, the best way to solve an inequality like this, I think, is to put all of the zeros of the left-hand side expression on the number line. So what values of x make this left-hand side equal to 0? Well, one of them is 7, and the other one is -7. And then we're going to just test points. I'm going to pick a number bigger than 7, like 23. 7 minus 23, I don't care what it is. I just care what the sign is. 7 minus 23 is negative, 7 plus 23 is positive, and then negative times a positive is negative. So it's negative over there. It's equal to 0 right here, and I want it to be equal to 0. So zeros, I want to include the 7 because, right, if I plug in 7, I get 0, which is okay. What's the square root of 0? Everybody, what's the square root of 0? Right, what's the square root of 1? Okay. Right, those ones always people, sometimes people leave square root of 1 as just square root of 1. Square root of 1 should always simplify to 1. Square root of 0 should always simplify to 0. Pick a number between -7 and 7. If I have a negative number and a positive number I'm picking between, I always pick 0. Question. So what I'm doing here is I'm saying, I want to know what's the sign of 7 minus x times 7 plus x. So over here, I picked a number. I picked kind of sillily x equal to 23, but the more typical choice would probably be like x equal to 8. And if we plug in x equal to 8, we're seeing 7 minus 8 is -1. 7 plus 8 is positive 15. And -1 times 15 is a negative number. So any number I pick over here would result in a negative product or a negative argument of my function, right? Because it doesn't matter if I pick 8 or 80 million. 7 minus any number bigger than 7 is always going to be negative. 7 plus anything is any positive number is always going to be positive. And the negative times the positive is always going to be negative. And then we're going to do the same thing here. We're going to pick, I would pick x equal to 0 if I'm between a negative and a positive. If I plug in 0, 7 minus 0 is positive. 7 plus 0 is positive. And a positive times a positive is positive. So anywhere in here, the result's positive. I could have picked 0. I could have picked 6. I could have picked -6. I could have picked pi. Any number in there is going to get the same result. And here's why. To change signs, an expression has to go through 0. And we've already identified the only places where it's equal to 0. So the only place where this function or this argument of this function can change signs is either at 7 or at -7. Anywhere else it can't, because it doesn't go through 0 anywhere else. That's why we identified the 0, so that we are kind of limited how much we have to check. So you might pick 0, and you might pick 6, and you might pick -5, and all of us will still get the result that this whole expression is going to be positive when we pick anything between -7 and 7. And just to exemplify that, I want all of you in your head to pick something other than -8 that's less than -7. Pick a number in your head, and then ask yourself, what's 7 minus that number? Is it positive or negative? What's 7 plus that number? Is it positive or negative? And then if you multiply those two things together, is the result positive or negative? All right. Give me a thumbs down if you got negative. Give me a thumbs up if you got positive. I'm like, what am I getting? I think it's negative, right? Negative. I was just leaving my thumb up like that. Let's see. Let me check. Let me do mine. I picked -9. 16 times -2 is negative. Yeah, it should be negative. And we all should have gotten the same result, because if 7 minus a negative number is certainly going to be positive, and 7 plus a number that's more negative than -7 has to be negative, and a positive times a negative is for sure going to be negative. Okay. Also, I want to make sure I include the -7 there, because if I plug in exactly -7, the whole thing equals 0, and we want to include where it's equal to 0. So now we have to remember what we're doing. I'm trying to solve the inequality 49 minus x squared is greater than or equal to 0, which means I want this left-hand side to be negative or positive. If I want to be greater than 0, do I want to be negative or positive? Positive. So I want the parts where it's positive. I want that part. I want all of this. I don't want any of that. So my domain for this problem is everything between -7 and 7, inclusive of the ends. So it's a bracket -7 to +7 with the bracket. And anything outside of that is not in the domain. If I plug in 8, 49 minus 8 squared is 49 minus 64, which is -15, and the square root of -15 isn't real. So it's 8 is not in the domain. And anything bigger is also not in the domain. 7.00003 is also not in the domain because it's just a little bit too big. Let's do one more like this. Let's not, because I don't have a lot of time left. I do want to talk about the last one. So the other type of function that has a very, very similar way of finding the domain is a logarithmic function. So if our function was, say, g of x equal to the log base 3 of, what do I want here? Sure. I want minus plus negative x squared plus 5x plus 6. So very similar to square roots, where you can't take a square root of a negative number. For logarithms, we can't take the logarithm of a negative number, and we also can't take the logarithm of 0. This is not defined. So for a logarithmic function, we need the argument to be strictly positive. So we're going to set the argument, in this case, negative x squared plus 5x plus 6, to be strictly greater than 0. And normally I would just say, let's factor it right off the bat. But I really don't enjoy factoring a quadratic when the lead coefficient is negative. So I would either bring everything to the right side and write it as 0 bigger than positive x squared minus 5x minus 6. Or if you prefer, which will result in the same thing, multiply both sides by -1. If you multiply both sides by -1, you're going to get positive x squared minus 5x minus 6 is less than -1 times 0. Right? Because you multiply by a negative, you have to change the order of the direction of the inequality. Look, these are the same. I know they look slightly different, but they mean the same exact thing. This means x squared minus 5x minus 6 is less than 0. This means 0 is greater than x squared minus 5x minus 6. But those are the same things, just said slightly differently. So now that we've got this in a nicer way to factor it, let's go ahead and factor it. X squared minus 5x minus 6 factors as x minus 6 times x plus 1. I want numbers that multiply to -6 and add up to -5. And those fit the bill. -6 and +1. So then on my number line, I'm going to plot the zeros of this left-hand side expression. The zeros are +6 and -1. Those values of x make this left-hand side equal to 0. Those are the places where the sign can change. Then we're going to do the same thing. We're going to test values. I'm going to test a number bigger than 6, like 7. 7 minus 6 is positive. 7 plus 1 is positive. Positive times a positive is positive. And then I'm going to test. I'm not. Interesting. Oh, yeah, that's fine. Is that fine, James? That's fine, yeah. Sorry, yeah. Sorry, it's fine. I wanted the result to be different, but it's okay. I was thinking backwards. And then pick something between -1 and 6, like 0. 0 minus 6 is negative. 0 plus 1 is positive. Negative times a positive is negative. And then finally, pick something less than -1, like -2. -2 minus 6 is negative. -2 plus 1 is negative. And then negative times negative is positive. We don't want the endpoints this time. And which parts do we want? The negative parts or the positive parts? We don't this time. So we have to be extra, extra careful. We started off by saying this. But then the inequality that we were actually solving was this one, where we want x squared minus 5x minus 6 to be less than 0. So be really, really careful here. That is maybe a reason why you wouldn't change it. I would still change it. But if I'm solving x squared minus 5x minus 6 is less than 0, then I need the negative part here. So just be super careful. Yes, we still want the inside to be positive, but the inside to being positive means the opposite of it should be negative. So we want this part here. So our domain here should be everything from exclusive -1 to +6. So everything up to like 5.999, everything down to like -0.99999, everything in between. So for example, if you plugged in 2, you'd have log base 3 of -2 squared plus 5 times 2 plus 6. Okay, here's a tricky one. What's -2 squared? What are we doing first? The exponent or the negative? The exponent. What's 2 squared? And then the negative of that is -4. If there aren't parentheses here, you have to do the squaring before you do the negative. So this is actually equal to the log base 3 of -4 plus 10 plus 6, which is the log base 3 of 16 minus 4, which is 12. The point being that this is a real number because it's the log of a positive number. So +2 that we plugged in is certainly in the domain of this function because when you plug it in, the argument of the logarithm is positive. That's what we didn't have to do that to check it, but I just wanted to show you. All right, it's 11:52. I should stop talking. I should have stopped talking 2 minutes ago. I will try to end on time. I just didn't want to leave you without talking about the last domain thing. See you on Tuesday. Seems like a long time from now. Definitely make sure you do. Oh, the other thing, the reflections don't last forever, meaning you have to do them the week that they are assigned, then they go away. You can't make them up later. So do the reflection. There's one that's currently up. I don't remember what day it's due. It's probably like October 3rd or something, but do it sooner than later. Do it over the weekend so you can tell me what you want to see me talk about on Tuesday.